Hi, I am Ahmed Daud, and in this session we will see some other regression or evaluation metrics for the regression models. So, in the last sessions we were doing some evaluation metrics and we have done like mean absolute error, mean squared error, root mean squared error, and what are the differences and the advantages, disadvantages they have. We have learned in the last sessions. So in this session, we will explore coefficient of determination and or some way you will listen R square metric. Okay, so R square or coefficient of determination. We will see this metric today and another metric which is somewhere related to the R square. It is called adjusted R square. Okay, so when you will see this linear regression documentation and you will see from here, yeah, this one, this score, the score function that is provided by the linear regression class, or you can say this model provided by scikit-learn. It when you will open this, let's say here, yeah, here you can see this is score and return the coefficient of determination. The exact metric that this class has used or this score function use we will learn today theoretically, and also we will try to implement that in the code. So here you can see here it's just a description of that coefficient of determination. So from here we will do it on the pad so that we can get an idea clearly. So here, okay, as I said, coefficient of determination, and somewhere we also call this coefficient of determination as R square. Okay, in somewhere you can see in this way R square. Okay, R square. So before going to towards that, I want to start from here. Let's say you have this data set. If I will zoom in, okay, you have this data set and the data set that we are still using in these sessions, area on the x-axis, price on the y-axis. For example, you have a model and model is just a very simple model which is y bar. Okay, so here you can say price bar. Okay, the average of a price. Okay, here you can say the mean of price. Okay, so let's say it is approximately 6.30 here you can say. Now let's say you have a very simple model, no need to do training, no need to do some computation, complex computation, and no need to run such algorithms on that. Simply you have to take the average of your target variable, average of your target variable here, and you will get a mean. Okay, now you will use this mean as your model. Like here I have used this mean, this is my model. Okay, which is simple model and it has it is, you can represent it by y bar. Okay, normally you have a model like that, uh, yeah, like that. You normally have the model like that and you represent it y by y cap. Okay, but here you have this model. Okay, now here if you are designing some model and your model is bad than and giving the bad accuracy or less accuracy than this model, this very simple model, then you can say the model that you have achieved is very ridiculous or absurd or very illogical. Okay, so you maybe there is a problem in your model training process, or maybe there is problem in your model selection. Okay, so you can use this y bar model, or you can say mean model, for your you can say as a threshold you can use it. Okay, like your model should be, any model you are training here should be greater or giving the accuracy greater than this model. Okay, because you know it's very simple model, just a average. If it is giving a good result, then why we need to go towards the some sort of other model? Okay, we should have other model that is giving good accuracy than this model. Okay, till now you have got an idea about, let's say this is a model. Okay, so here now you have some errors. Okay, like we have in all the type of models, we what is our actual value? Our actual value, like here, our actual value is this one, and our predicted value is this one. Okay, we have a error one. In the same way, the predicted value is this one, actually is this one. Error 2, error 3. We have five errors, like we have five sample points here. Okay, we can say each error as a, here you can consider total error. Okay, the total error between actual and the prediction. Okay, so total error 1, 2, 3, 4, 5. And like the same way as we do to ignore the sign, we are taking squares at this side. Okay, and now we are adding our sum of squared total errors. Okay, in this way. Okay, so here you have this sum of squared total error, or you can say SST. Okay, which is just a you are subtracting from each point your mean. Okay, because mean you have considered as a model, and when you will present it in the form of sigma, and you will have this type of or error function here. Okay, SST. And if you can recall, just take a mean of that SST. It will be mean of sum of squared total errors. This will become, and you can see it is exactly the same as variance. Okay, or in other words, you can say it is also the formula of variance that I have explained in some other way. Okay, I have considered here y bar as a model. Okay, and you can say this y bar is like a model that is that can be used as a threshold. Okay, if we will train another model, the another model should have accuracy greater than this model. Okay, now as we are learning from the last sessions, like we usually use sum of squared error. Okay, so here we have, if we have this model, like this model we have here, or y cap, which usually we are representing in this way, mx plus c. Okay, so if I will make it yi. Okay, and these m and c that we have to find in during the training process. Okay, so if this model is here, and if we will calculate the errors for that, then you can see here the errors will be in this form. Okay, if I will use another color here. Okay, now we have a sum of squared error. This is sum of squared error, and if you will take a mean of the sum of squared error, you will get MSC. Okay, now you have seen one error you can call as SST, which is sum of squared total errors, and one is sum of squared errors. Okay, two errors you have. Now when you will see the formula for the coefficient of determination, the formula is like that: R square is equal to 1 minus SSE divided by SST. Till now maybe you have got the idea how this R square works. Okay, now I will explain you visually. Okay, let's say sorry, this one. Okay, so if I will remove this from here. Okay, let's say I will remove this. Okay, uh, okay, so here you can see this is y bar, this is y cap, and this is your actual value. Okay, now your total error that you have considered as your total error, and for that you have used SST. Okay, like total error 1, total error 2, in this way. Okay, you have used SST, which is also similar to variance. Now the second one is that you have considered error 1 plus error 2. Okay, all in the this is also in the form of squares. Okay, and this is also in the form of squares, and you have considered it as a sum of squared error. Okay, now you will see from this part to this part, it is a y minus y cap or y bar. Okay, you have considered it as a error. Let's say error 4 in this case. Okay, and when you will take square it will be in this way. Now if you will calculate your error, this is your actual value. Sorry for it. Okay, so this is your actual value, which is y, and this is your prediction by y cap. Okay, minus y cap. Now this is another error that you have considered as a SSE. Now you can see your total out of your total error, out of your total error. Okay, out of your total error, how much error is reduced by using this model. Okay, now you can see here your total error was this so much, and now after using this red model your error is this one. Okay, now you have this error. Now just the ratio, when you will calculate, you will consider this as a total error, this as a total error, and this as a the error that we still have after having a model. Okay, error still have after a model. Okay, now the ratio of this error, which is SSE divided by SST, will say you how much portion of the error you still have out of total error. Okay, when you will make this 1 minus SSE out of SST, this will describe you how much error you have captured till now. Okay, how much your model has explained the variation in your data till now. Okay, this part is telling how much error still you have. Let's say your total was if I will, if I have here, yeah, like this, if your total error was 100 and now you have a 20, then it is like this SSE over SST will become 0.2 if I am not wrong. uh, yeah, 1 over 5. Okay, now 1 minus 0.2 is equal to 0.8. Your R square is here 0.8. Now you can say your model here, your red model, this one, your model Y cap. Let's say your model has explained the 80% of the variation in your data, or you can say the how the variation in the price column, which is your target column, is the total error. SST is the total error, this one, and your model has explained the 80% of your total error. Okay, in this way you can consider that R square is very good in the way of explanation. You no need to explain the data or your accuracy of your model in the context of your target column. Like in the last sessions we usually explain our metric in this way, like in the case of MSC or MAE, we explain like this model has an error of 1.2 lakh, 0.1 lakh, 11,000. Okay, we are explaining in this way in the context of target column. But if we want to such a metric that can explain how much our model is good in without the context of target column, like our model is 80% good or 90% good. Okay, so this R square can help us and can explain in that way that we want. Okay, R square tells you how much variation of your target column is explained by your model. Okay, as this model is mm, yeah, as this model is just a mx plus c. Okay, so this is independent variable. You can say that how much R square will explain you how much your model explained the variation in your target column. Or in other word, you can say R square explains the variation of dependent variable by independent variables. Okay, R square explains uh, in this way. Explain the variation of your dependent variable by independent. How much independent variables are explaining your the variation in your dependent variable. Okay, in this context, R square works. Okay, okay. Now it has a range from 0 to 1. You can consider from here. You can see from the formula. Let's say your formula is this one: R square is equal 1 minus SSE, and you have considered SST as your total error. R square will have a range 0 to 1. If R square is equal to 1, then it is good, or you can say excellent. And if it is close to 0, then your model is bad. Okay, when it will get the answer close to 0, when your SSE is approximately equal to 1, you will approximately equal to the SST. Your this part will become equal to 1, and 1 minus 1 will give you a 0, and R square is equal to 0. In this way, you can say your model is bad. If SSE is very low, approximately equal to 0, if I will make it here, yeah, if your SSE is approximately equal to 0 and divided by SST, your this term will become 0, and 1 minus 0 equal to 1. Then you can say your model is very good. Okay, here you can say very good, or you have a good model here. Okay, now it has a range from 0 to 1. Unfortunately, if your sum of squared error, if I will make another here, sometimes you got an answer of R square less than 0. Okay, sometimes you can get a R square less than 0, or you can say negative value. The reason for that is that when you have SSE, when you will get SSE greater than SST, which is obviously a very bad model. Like if your model is giving us such a bad or more error as compared to your very simple model, as compared to very simple, this is very simple model which is y bar, and here the model is y cap. So if your model is trained model is giving a very large error as compared to your just a mean model, then this term will be greater than 1, greater than SST, and this term will be greater than 1. Okay, when 1 minus greater than 1, let's say 1.5, then your answer will be in the form of minus 0.5. And there must be such a problem in your model. Okay, there is a must be some problem. Maybe the problem is your model, the model is giving very bad accuracy, or very high error as compared to uh, very simple model which is SST, which is just a mean of the target column. Okay, you have got an idea how R square is good in the context of explainability. It is good. It explains how much variation in your target variable, in your target your target column is explained by the model. How much variation is explained by the model. So that's why SST also I told that SST is similar to the variance. Okay. Now there is another question that we usually raise, is that is about the disadvantage of our R square. So R square, as you can see, it is 1 minus SSE over SST. In SSE, the model is y cap. In SST, the model is y bar, and y cap we know usually is like that, mx plus c. Okay. Now, the biggest disadvantage is that when we have some irrelevant feature, which is irrelevant, and we are using during our training process, our R square is increasing. Okay, or maybe it will not change or it will increase with the adding some irrelevant feature, but it should not increase actually. Okay, because of irrelevant feature is has no importance in the our explanation of target variable, so it should not increase, but it is increasing, still increasing. Maybe some of you can have a question in your minds, uh, why it is R square is increasing. Okay, yeah. So um, I will explain in this way, but I will tell you that you should think about that why R square is increasing by adding some irrelevant feature. I will give you some hint. It is the reason is that due to this we are using a regression model, and in this regression model, when you will add uh, some another feature like this one is m1 x1. Let's say you will represent this in the way y cap is equal m1 x1, and I can write in this way m0. Okay, so if you will add some another feature, it will become m2 x2 plus m1 x1. This equation will come in this way. Okay, if your addition of this feature, that say it's a irrelevant feature. Okay, irrelevant feature. So due to the nature of the equation, the nature of equation is that if it is completely irrelevant, it has no relation with your prediction, then it will make m2 equal to 0 approximately. If it has some sort of a little bit relation, then it will give a very small value to this m2, small value. And if it is relevant to the prediction, then it will give some a large value to this. Okay, I will let on you, or I will recommend that you should think about that why r square is increasing by increase of the irrelevant feature. Okay, but for now, r square is increasing due to increase in irrelevant feature. How we can avoid that? There is another, you can say, some we are tweaking some formula of r square, or adjusting our formula of r square, so that we can also um, compare that how much our model is uh, by adding some irrelevant feature, or by adding some feature, how much the accuracies are affecting. Okay, by adding some feature. So we should also we will design such a formula by just adjusting this r square formula. Okay, that's why we usually call the next metric as a adjusting r square method. Okay, so so here we have a formula for adjusted r square. We have just make some changes in the already the r square that we are using, that can cater the number of samples and number of features also, so that we can see how much our accuracy is increasing with the increase of feature. If the feature that we are increasing or that we are adding are irrelevant, then our adjusted r square will be decreased. Okay, if our the added feature is some sort of relevant and have some some importance, or you can say explaining the your target column, then your adjusted r square will also increase. Okay, now there will be a trade-off, how much your uh, accuracy will increase by increase of feature. Okay, by adding some addition of some feature. So here I will explain you here. This is a Yeah, this adjusted R square, the formula is simple. Y minus y, here r square 1 minus r square. The r square is the the r square that we have calculated before, which is r square is equal 1 minus SSE divided by SST. Okay, so n minus 1 divided by n minus k minus 1. So n is equal number of rows or samples and k is equal number of independent features. Okay, so here we have this formula, and this formula will cater that if your number of features are increasing, then it will if the increased or the new added features are irrelevant, then the adjusted r square will decrease, and if relevant it will increase. I will show you how it is it's going on by this formula. Okay, so I will explain in this. Here your formula is for the adjusted r square is equal 1 minus 1 minus r square n minus 1, and here n minus k minus 1. This is k. I will make it this way. So here I will consider for the irrelevant feature. If the added feature that we are adding here is irrelevant. Okay, so if our feature is irrelevant, then our k is increase, because let's say if before we have two features, we have added one feature more, our features will become three. Okay, if before we have two features, we are adding another feature, independent feature. Now we have three independent features, so our k will increase. If the added feature is irrelevant, then r square will increase, but not so much increase. Okay, it will increase, but this increase is very low. This increase is very low, so that's why we will neglect this. Okay, because this increase is more as compared to this increase. Now what will happen if this increase, this will increase, k will increase. Now this whole term, the denominator will decrease here. If this will decrease, our whole answer for this square bracket will, if this denominator will decrease, the uh, the the answer for this whole square bracket will be increase. If this will increase, so 1 minus increase, you can say our over adjusted r square will decrease. Okay, in this way, with the addition of irrelevant feature, our adjusted r square usually decrease. Okay, usually decrease. Now if our feature is relevant, if the feature will be relevant, then what will be the effect adjusted r square will have? So here adjusted r square 1 minus, here you have n minus k minus 1 here, and here you have 1 minus r square, and here you have n minus 1. Okay, the same this one. Let's say you have here, before you have k is equal to 2, now you have k is equal to 3. If the added feature is relevant, okay, now of course it will increase your accuracy r square too much, so it will increase a lot here, but there will be increase, just increase of 1. There will be increase, but this increase will be low as compared to the increase, as compared to this increase. Okay, now if this will increase 1 minus increase term, so this, the upper term will be overall will decrease. This upper term overall will decrease. If this term will decrease, then the here will be the answer of whole square bracket will decrease. If the answer of whole square bracket will decrease, then 1 minus decreased term, it will give you a more score as compared to the score that we have before. Okay, in this way, it will cater for the it will also cater the how many features we are using, and with the addition or with the dropping of feature, how much our score is affecting. Okay, there is a trade-off. If the feature added feature is giving so much accuracy, okay, or is it important to add this feature because it is enhancing our explainability or enhancing the score of our model. So this is about the adjusted R square. Now we will see this in the form of code. Then you will get more idea about the how R square is increasing with the increase of irrelevant feature and how adjusted R square is not increasing. Okay, and for R square, how R square is good because the way of explanation by R square. Like if the R square is giving 0.8, then you can say 80% variation of your target column is explained by the model that you have, or you can say that you have trained. So now we will try to code the score and try to see the difference of R square and adjusted R square by the addition of some irrelevant feature. We will explore that, and we will also see how we can calculate this score R square, and in which way we can explain R square. Okay. So first of all, you know about this one. This is the code that we are still using, and in the last session we have seen that this is our model. This is x-axis, y-axis, and we have seen the mean absolute error. In the same way, we have seen the others also, mean squared error and root mean square error. Today we will see coefficient of determination. So this is our area, which is independent variable. This is a dependent variable price. Now, okay, so before that, I will show you here in this, yeah, this one is score. We can use this score by using the model that we have trained. Okay, so here the model is our linear model, LR model that we have trained here. If I will show you here, yeah, this one that we have trained here, this one. Okay, so this model we have trained. Now this model already have the values of coefficient and intercept. Okay, so it has the parameter values already. Now how we can use this score function? Here you have LR model that you have trained dot score function, and here you will pass the independent features, okay, and your true values. Okay, by using the parameter values that it has, it will automatically will calculate the predictions of against these areas and this and compare with these true values. Okay, now it has calculated the score. This score is R square. Okay, 0.958. Okay, this is R square score. If I will zoom in, okay, you can see here clearly. Now I will add a irrelevant feature. The irrelevant feature here I am adding, it's a for sale. Now for the context, you can understand for sale cannot predict who or should cannot explain what should be the price of house. It's a contextual way, or you can say conceptual way. You can say for sale should not be a uh, feature for the explanation of price. What should be the price? But anyhow, accept that, accept the learning of, or accept explaining the domain in which domain we are talking about here. But if we will just rely on the numbers, so you can see for sale have these values 1 1 1 1 and 0. Okay, and here we have two independent features, for sale and area. By these two independent features we are trying to predict price. You have seen we have added this feature, and from the values you can compare that with the change of for sale. There is how price is changing, or you can say how the variation of for sale is explaining the variation of price. This is the scatter plot between the area and price. Here you can say there is some sort of relation between area and price. As area is increasing, your price is increasing here. As area is increasing, your price is increasing. When we will see the scatter plot for the fall sale and price, you can see here there is no you can say significant relation we can see here. Okay, because here at the one there are some values. Okay, These are the prices of the houses, and when the for sale will increase the value from 1 to 0, there is sudden increase in the price. So here we can say this, there is a some sort of negative relation between for sale and price column, but significantly you can see there is no a clear relation, very less relation, which is also negative, but you can see how irrelevant it is. Okay? Or you can say how this feature is not explaining so much the detail of your target column, so you can consider it as an irrelevant feature. So I have another model, linear model 2, and I am fitting here, and I am passing as a independent features as a this one far sale and area independent features, and dependent feature here will be price. Now the model is trained. Now when I will calculate the score for this, when I have added here, the score is 0.9586. This is R square score. Okay. So 9586, and our score without irrelevant feature is 9584. Okay. 9584. You have seen that by the addition of irrelevant feature, our score is increased a little bit, but it increase. Okay. uh, as I told you in last time in the start of session, that with the addition of some irrelevant feature, there will be some change or no change in the uh, r square. Okay, but there will be no chance that r square will decrease the score with the addition of irrelevant feature. Okay, the reason is that I have also recommended you to analyze the reason, and I have given you the hint that the reason is due to the nature of the formula of that we are using for the regression purpose. Okay, that we have the equation y is equal to mx plus c. Okay, we have some parameters. Okay, coefficients and intercept, or you can say we have some weights for each variable. If our variable is not so important, it will give the lower weight, but due to addition of some irrelevant feature, there will be no chance that our accuracy will decrease. Okay, by the nature, due to by the nature of formula, but we want such a formula that will affect by the addition of that will have a negative and positive both effects with the increase of features. Okay, if the feature will be irrelevant, it should have negative effect on the accuracy, or you can say the accuracy should decrease. If the feature is relevant, then there should be a positive impact on the accuracy. Accuracy should be increased. Okay, here you can see there is a little bit increase in your accuracy. Okay, which is 9586. Now there can be another question for you, that 9 from 9584 to 9586, by the addition of one whole column, you are getting a very less. Okay, up to fourth decimal position, you are getting some increase in your accuracy. So there is a trade-off by addition of a feature. How many percent or how much percent you are increasing your accuracy? Like here in this case, 0. It will be 0.02%. 0. It is not only, it is not 1%. Okay, it's less than 1% you are achieving by addition of one whole column. When you are adding one whole column, your training process will slow. Your prediction process will also come to slow, and your a lot of computation, if you have a very large data multiple columns, then it will affect a lot on the multiple aspects of your prediction and training phases. Okay, here you can see uh, with the increase of one irrelevant feature, there is an increase in the score of r square, which should not be. Okay, okay, here I want to tell you that with the like if you have some random variable. Okay, so random variable can also, if you will add in your data as an independent variable, and when you will train your model in case of r square score, in case of this score, again your model will give some better score as compared to without the random variable, or maybe equal to the last score. Okay, so random variable can be 2 to 3% or some lower percent can be have explanation to your target column, but it's not a you can say significant. So here we want such a measure that can badly impact by the addition of irrelevant feature. So here I have added another this is for cell column in which we have this value is 0. So I have created another data set data 5. Now I am going to make this 0 as equal to 1 so that there will be no change in the for cell column. So here you can say it's a it has no importance in this data set regarding the prediction of price because there is no variation in the for sale so that it can explain the variation of price. So when I have trained the model on this data set, where I have used for sale and area as a my independent features. So here I have used that. Now you can say the this is 95. This score I am getting here R square score here, but without the irrelevant feature we have this score. Again, very less increase in the score. Like here in the last decimal point you can say 487, here the 489, very less, but again there is a increase. But there should be such a measure that with the addition of this type of irrelevant feature our accuracy should decrease, but here it is not decreasing. Okay, it should decrease. Here you can say this variable, this partial variable has no variation in its data, and it is uh, not explaining even 1%, not explaining the variation of price. Okay, and the impact that I was saying that why R square is uh, like R square is not decreasing with the addition of irrelevant feature. The reason is that I have given you the hint. The reason due to equation of the regression model that we are using, and here you can see in the equation that when I have calculated when I have printed the coefficient of that model, here it is giving me the zero coefficient for this column for sale and 0.13 for the other column. Uh, Either during the training process, this model has recognized that this for sale is not explaining the price, so it has given the zero as a coefficient. Now this model this feature will have not any impact on the prediction, but anyhow if it is at 1%, if it will be 1% explaining the price, then there will be some 0.00 or something in the coefficient, and or you can say it is this model during its training process it will give some weight, some coefficient value to this variable if it has some sort of a little bit variation, but it has no variation, so that's why it has given the zero. Okay, so here it is also another hint or more clear hint for you why R square is not increasing, not decreasing with the increase of with the addition of irrelevant feature. Okay, because of the natural formula that we are using in SSE. Okay, so here come back how adjusted R square will work. So previously we have this score when we have no any irrelevant feature. So if I will run that, okay. So I have stored this score, which is R square score in the uh, R2 score 1. If I will make clear R2 score 1 in this variable, now I am using the same formula that we have 1 minus R1 minus the whole term 1 minus R square into n minus 1. So n we have 5 points n minus 1. So divided by n minus k minus 1. So n is 5. K is number of independent features. Here we have just one. So that's why it's 1. Now it will give our adjust score of adjusted R square, which is 0.944. Here you can see. Okay, I am going to copy so that we can compare. Now when I have added irrelevant feature here, let's say this one. This one when I have added this feature, now I will see the adjusted R square of this model. Okay, LR model. So here I have these two columns. Uh, you can say these two independent features. So that's why here n minus k is equal to 2 here. Okay, and R2 score is I am using the score that this model have. So this model has R2 square, this one. So here when but I am interested here in adjusted R square. So here you can say 0.91. Here if I will make here without without irrelevant feature adjusted R square score is equal to this one. Here you can say the R square is 0.94 for but with the addition of an irrelevant feature R adjusted R score is decreased here 0.91. You can see here, okay. So now you got an idea with the in this way by the use of adjusted R scale, you can also see the importance of your variables, how much variables are playing in the role of uh, the modeling or playing in the role of explaining the variation of your target column. So in this way, you can see the importance of your variables that you have. Okay, by addition of some variable, you can see the how much your adjusted R square is increasing, and by the change in adjusted R square, you can get an idea how much the feature is important that you have added. So here, for you, I can do it for the last one, in which we have a very bad irrelevant feature, which is which has no impact, totally no impact. It's just a constant values, and there is no variation in this variable. So when I have printed the adjusted R score for this, you can see here it is also or degrees and it degrees uh, less, like in that case it is 0.917 adjusted R score and here is 0.916. Here you can see this irrelevant feature is totally irrelevant. Okay, it has, you can say, zero relation with your target column. So as it is has a zero variation, and anyhow the upper one has this data set has a little bit variation due to just one value. So that's why it is giving 917 score here 0.917, and in that case when we have a very bad irrelevant feature we have 0.916. Okay, now you can say how much adjusted R square score explained you the variation they explained you the addition of irrelevant feature. Okay, so in this session, we have seen R square score. What is R square score? R square score is basically explain the variation of target column by your model. Okay. So for the formula context, you can see you have formula 1 minus SSE divided by SST. SST you can consider as a total error and SSE you can consider the column. Still you have after implementing your model. Okay. So in this way, R square explained how much variation you have covered till now and how much variation you have. So if the R square is 80%, or you can say the R square is giving the score 0.8, then you can say 80% of variation of your target column is explained by your model. Okay, so in this way, R square explained very well without the context of target column, like in the last errors or last metrics that we have learned, MSC, MAE, RMSE explained you the how much error you have in your target column in the context of the target column, like 1.2 lakh the error you have, 1.3 lakh error you have, or in that even in the MSC there also the change in the unit, but R square explained you without the context of your uh, target column. Last one, we have seen adjusted R square because there is one flaw in the R square score. The flaw was that it is not decreasing with the increase of addition of irrelevant features. So we have made some changes in the formula of R square. That's why we also call it as a adjusted R square. We have made some changes and add the some you can say some power to the formula that can cater the how many number of rows in the dataset we are using and how many number of columns we are using. Due to by the use of that power, by the using of power of n and k, adjusted R square can explain you the score with the addition of some irrelevant feature. If you are adding some irrelevant feature and you are calculating adjusted R square score, it will definitely will decrease. Okay. By using adjusted R square, you can also see the importance of the feature that you are adding in your uh, training process, or you can say that you are using for your modeling. So till now, I hope you got enough idea. I have also implemented in that this in the code, and I also recommend you to just it's not a big deal, but just have a some uh, thinking about that how R square is not affecting by the or R square is not decreasing by the increase of irrelevant features. Okay, so for now, thank you.